Welcome back. In the previous video, we introduced alternating series. And these are series where we alternate between adding and subtracting terms. One of the weird things that we saw about these is that they are not absolutely convergent. Think of the alternating harmonic series again. It's our favorite example that we use over and over. We showed that the alternating harmonic series converges, but if you take the absolute value of all the terms, you just get the usual harmonic series and it doesn't converge. What we're going to emphasize in today's video are many of the quirks of alternating series. And we're going to show that some things go really, really wrong when you don't have absolute convergence. So let's jump right in. So the first thing that I want to talk about is I want to give you a definition. And this definition is how we think about these alternating series. So a series that is convergent but not absolutely convergent. Is called, we'll put this in red to highlight it, it's called conditionally convergent. Okay, so again, think about that alternating harmonic series. The alternating harmonic series using this definition is conditionally convergent. In fact, we can take this even further. Let's look at all of the sums, all of these p sums, the alternating p sums. Okay, so there are two cases here, right? If p is bigger than 1, then these things are absolutely convergent, right? We've talked about these quite a bit. When you take the absolute value of the terms, you get just the sum over 1 over n to the p, which is finite, which implies absolutely convergent. Right? So because it's absolutely convergent, the original series, the alternating p series with p larger than 1, is itself convergent. Okay, how about another one? What happens if we take p between 0 and 1? So we've already seen that this thing, the original series, is not absolutely convergent, right? We've done a lot of work with this stuff. But if we remember the notation from the alternating series test theorem, un would be 1 over n to the p and satisfies the conditions of the alternating series test. Which implies the series is convergent. And therefore, we are conditionally convergent. And you notice that this includes the alternating harmonic series, right? The case when p is equal to 1. So this is weird, right? We know that when p is between 0 and 1, without this thing alternating, so the absolute value of these terms, this thing converges. Or sorry, it doesn't converge, pardon me. But we now know from the alternating series test that it actually will converge if your sequence here is alternating. So that's kind of weird, right? It's very, very quirky. Now, what I really want to talk about is what I think is one of the coolest, sort of most interesting results that comes with these conditionally convergent series. And the way that we're going to think about this first is from what's called the rearrangement theorem for absolutely convergent series. So let's start with that theorem, and then I'll give you an example of sort of why that theorem doesn't apply to conditionally convergent series. Okay, here's the theorem. So again, this is the rearrangement theorem for absolutely ABS, so that's my short form, convergent, CONV series. I just want to be able to fit it all on one line. Okay, let's imagine that we have a series, and this thing is absolutely convergent, or is absolutely convergent. And let the sequence B1, B2, B3, so all the way up to Bn, keep going. This is any rearrangement or any arrangement of the sequence An. Okay, so for example, if I have A1, A2, A3, A4, right, that's my usual sequence. I'm summing them up in that order. This is saying that I can switch the orders, right? Maybe I can start with B1 is A100, and then B2 is A1000. All that matters is that I reordered these things. And this tells me that my sum of Bn's converges absolutely as well. And that it converges to the same thing. Okay, so maybe you're not impressed, and you probably shouldn't be, because what this says is that order doesn't matter, right? That's essentially what this is telling you. So if you're summing things up with a specific order with the ANs, what the series in Bn's is saying is that you can sum it up in any order you like, and it's still going to give you the same sum. Now, when we have finite sums, this is always the case, right? 2 plus 3 is the same as 3 plus 2. 2 plus 3 plus 4 is the same as 4 plus 2 plus 3, right? It doesn't matter how I reorder those things. I always get the same sum. So, you know, this theorem is kind of just telling us what we probably already assumed to be true. But I want to emphasize something. This requires your series to be absolutely convergent. If you are not absolutely convergent, then things fall apart. In fact, there's an old theorem due to Riemann where you can show that if you have a conditionally convergent series, so not absolutely convergent, then you can reorder the series to converge to any number you want. Think about that. Let me repeat that. If you have a conditionally convergent series, you can reorder it to converge to any number you want. It can converge to minus pi. It can converge to plus pi. It could converge to pi to the 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 e. I don't care, right? It's a number. That is absolutely insane. And this is why conditionally convergent series are not great, right? Because order matters with conditionally convergent series. Now, I'm not going to prove Riemann's theorem, but I want to illustrate it with you with our old friend, the alternating harmonic series. So what do we have? Let's consider, I'm going to show you how to make this, to rearrange it so it can sum to something that doesn't make sense. We've already proved with the alternating harmonic or with the alternating series test that this thing converges. So in fact, I told you it converges to the natural logarithm of 2. Well, we can use the approximation theorem to find out that the sum, so let's say if L is equal to this summation, over n, we can use the alternating series approximation theorem. So that was the second theorem from the previous video. I might have the name slightly off. To find that, 1/2 is less than L, which is less than 5/6. Okay, so it's somewhere between 1/2 and 1, right? It doesn't really matter. The thing is, it's not really important what the actual value is, but in particular, all that really matters is that, clearly the limit of this thing is not 0. Okay, let me show you why things can go bad. Okay, so first of all, if L, so we know L is equal to this series. So this is 1 over 1, so which is 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. I'm going to extend this out a little bit. I'm going to multiply by 2, right? So I'm going to multiply the left side by 2 and the right side by 2. So now I get double whatever that limit was. So 2L has to be equal to 2 minus 1 plus 2/3 minus 1/2 plus 1/5 minus 1/3, and so on and so forth. Actually, let me put more terms in there just so I can really drive this home. 2/7 minus 1/4 plus 2/9 and minus 1/5 and plus 2/11. Okay, so I simplified all the fractions as I went. And let's see what we have now. Okay, so my rearrangement here gives me, I'm going to group some terms together. So 2L is equal to 2 minus 1. Okay, so I'm going to group the two first terms together. Then I can see, maybe if I circle these, there is something with the denominator 3 and something else with the denominator 3. So let's put those two together as well. So this is going to be plus 2/3 minus 1/3. Okay, so that's fine. Then maybe I'll use a different color. Let's go with, oh, I'm sorry, I forgot the 1/2. Pardon me. I skipped all the way up. So there's minus 1/2 here first, and then the 2/3. Sorry. 2/3 minus 1/3. Okay, so that's good. Maybe we'll circle off the terms that we've already used. So there's that one. We used this one and this one already. Now, the next numerator that we are interested in is 1/4. There is only, or 4, there's only one of them. So there's 1/4. That's coming from the 2/8 term. So that's right up here. Okay, then the next one is going to be denominators of 5. I just noticed I have a mistake here. This should be 2/5, not 1/5. Sorry, 2. So then we're going to do the same thing. We have 2/5 minus 1/5, just like we had with the 1/3. And then minus 1/6. And I'll just do the next one. This is going to be 2/7 minus 1/7, and so on and so forth. Okay, so what was the point of doing all that other than just maybe making it tedious on ourselves? Well, let's simplify it. 2L is equal to, so the first term becomes 1 minus 1/2. The next term in the brackets becomes 1/3, 2/3 minus 1/3. Okay, and then minus 1/4. And then plus, what's this? We have 1/5 now. 2/5 minus 1/5, minus 1/6, and then plus 1/7. And if you wanted to, this would be minus 1/8, and it would keep going. Sure. Okay, that's fun. What happened though? I got the original harmonic series. This is the alternating harmonic series again. So here we have the alternating harmonic series again. And so this tells me that 2L, which never changed on the right-hand side or on the left-hand side, is equal to L, because L was the sum of the alternating harmonic series. But the only way this can happen is when L is equal to 0. But we already know L does not equal to 0. So this is really, really weird, right? And why did it screw things up, right? Why did it go wrong? Because let me show you with red here, this step from here to here, we rearranged the order, right? I took this 2/3 and moved it back here and pushed the 1/2 up here. I moved the -1/3 forward and moved this 2/5 back. I took this 1/4 and I moved it forward. And then I took this -1/5 and also moved it forward. So the red arrow on the left here is indicating that I rearranged the series. And by rearranging the series, everything fell apart, right? Because I said that the only way that I could ever make this work is if L is equal to 0. So that's just a sort of warning about where things can go wrong with alternating series, and in particular, conditionally convergent series. Unlike absolutely convergent series, where order doesn't matter, conditionally convergent series, the order matters. They are written to you in a precise order. You have to add them in that order, or else you can get something completely different, things that don't make any sense. And we saw an example of this with the alternating harmonic series, where I got a logical contradiction, right? I said that the sum of this thing, which again, we know is about the natural logarithm of 2, I found that it's actually equal to 0. It's really, really strange, right? I think this is one of the most interesting results in mathematics, and it shows kind of why we want to avoid working with conditionally convergent series. And it should further reinforce for you why all of those convergence tests are all in terms of the absolute values, right? Or we assume that the terms are non-negative. This comes from the fact that we care about absolutely convergent series. And those are the types of ones that we really want to work with as much as possible. And that's where most of the convergence tests are built up.